Blending allows the colour output from the pixel shader source pixel that we are currently rasterizing and the colour of the destination pixel in the back buffer to be blended together into a new colour that will overwrite the destination pixel's colour. You can see that here in the water. Blending operators and blend factors are set in the blend state. The blend state is part of the PSOs here, and you can see the default blend state being used here. To configure a non-default blend state, a D3D12 blend desk struct has to be created. Alpha to coverage enable is a multi-sampling technique that is useful when rendering foliage and gate textures, for instance. Independent blend enable means that blending can be formed for each render target differently, as Direct3D supports rendering to up to 8 render targets simultaneously, and multiple render targets are used for advanced algorithms. Render target contains an array of 8 D3D12 render target blend desk elements, where each element describes how blending is done for that specific element's simultaneous render target. By setting different combinations for the source and destination blend factors, along with different blend operators, you can create lots of different blending effects. You can see the different blend factors for transparency set here. You can change the render target mask here, for instance, to only write blue to the back buffer after blending. There are many techniques you can do with different blend factor combinations. For instance, adding and subtracting source and destination pixels, which for example can be used to make brighter and darker images respectively, multiplication of source and destination pixels, and no colour right, which leaves destination colours the same. Transparency is a technique which is done by letting the source alpha component control the opacity of the source pixel. For example, the water's alpha here is 0.4, making it 40% opaque, and changing this changes the transparency. This is achieved by setting the source blend factor to D3D12 blend source alpha, the destination blend factor to D3D12 blend inverse source alpha, and the blend operator to D3D12 blend op add. This makes the blending equation make colour equal to alpha source times the source pixel colour plus 1 minus alpha source times the destination pixel colour. It is important opaque objects that don't use blending are drawn first, and the objects that do use blending are drawn after in a back to front order. The reason for this is that for an object to be transparent, the pixels behind it need to have already been written to the back buffer, so that the transparent source pixels can be blended with the destination pixels behind it. If I change the render order by editing the command list to make transparent render first, you will see that the water is no longer transparent. When we want a source pixel to be rejected from being further processed, we can use the intrinsic HLSL clipX function. This function can only be called in the pixel shader, discarding the current pixel if x is less than 0. This is used when rendering the wire fence texture on the cube, where pixels with black alpha channels are rejected. We can see this here in the pixel shader, where we take the texture's alpha component, and if the value is less than 0.1, meaning transparent, we clip the pixel from further processing. The same result can also be achieved using blending, but clipping is more efficient as no blending calculation is needed, and the draw order does not matter. Also, by discarding a pixel early from the pixel shader, the remaining pixel shader instructions can be skipped. The fog effect can be used to simulate different types of weather conditions in games. For instance, I can change it to make it appear to be a sandstorm. Even scenes set on clear days use fog to make distant objects like mountains appear hazy. As well as this, fog is used to mask distant rendering artifacts and prevent popping, which is when an object that was previously behind the far plane suddenly comes in front of the frustum due to camera movement, becoming visible and making it seem to pop into the scene abruptly, so having a layer of fog hides this. Fog colour, fog start and fog range being how far from the fog start distance it completely hides objects, are specified here in the constant buffer so it can be changed mid-scene. Fog doesn't alter the colour of vertices that distance is less than fog start and completely hides the surface points at distances after fog end, with fog end being fog start plus fog range. The thickness of the fog increases linearly between fog start and fog range, so as distance increases, the fog colour gets more weight, while the original colour gets less weight. You can see fog being implemented here in this shader code, as well as down here. Fog is made optional by requiring fog to be defined when compiling the shader, which you can see here. This way, if fog is not wanted in a scene, fog calculations aren't needed, which saves on resources.